Hello, this is my presentation on torques. My name is Tyler Bush, and the goal of this presentation is for you to have a better understanding of torques and know some real-life examples that utilize torque. So we're going to be looking at real-life examples and also looking at torques from an analytical standpoint as well. So, first question, what is torque? Or what is a torque? Let's start off with some definitions first. So we have translational motion, and translational motion is when an object's center of mass moves from one point to another, and this is caused by net force. Then we have the rotational counterpart of that, which is rotational motion, and this is an object moving about its center of mass. And aside from translational motion, that's caused by net force, rotational motion is caused by net torque. This is an example of translational motion. I am moving the skateboard from point A to point B. This is an example of rotational motion and translational motion. The skateboard is going from point A to point B, and the wheels are also turning, which is causing rotational motion. And right here I am demonstrating putting a torque on the wheel, and I apply a negative torque to stop the wheel from moving. So the definition of a torque is the influence changes the rotational motion of an object. And we have the formula for torque, which is just this symbol right here, which is tau, is equal to r perpendicular distance times the force, right here. And then the units for torque are going to be Newton meters, and that is also equal to joules, but since that's usually for a work and power problem, you would be using joules, but for torques, Newton meters. This torque is equal to the force applied multiplied by the lever arm. And this is an example of a torque problem. This is going to be our wrench, and this is a nut or a bolt that we're trying to tighten. And we're going to be applying a force from the handle on the far end of the wrench. And this is the lever arm. So you would do force times lever arm, and that would give you the torque that you would be applying to this wrench. Real life example of using a wrench on a bolt to try and tighten or loosen a bolt. If you wanted to tighten it or loosen, you would have to apply the force on the farthest way you can from that hinge point to get the maximum torque possible. And now I'm showing if you applied the force closer to the hinge, you're going to have a lot harder time because you're going to have a lot less torque. Here's another example with the door. The doorknob is on the opposite side of the hinge because that's how you get the most torque. And the lever arm is going to be from that hinge to the doorknob. Alright, here I am showing opening. It's pretty easy. And now I'll be showing applying a force very close to the hinge. And you're going to need a lot more force to open that door the closer you are to that hinge. Alright, here's another example of, this is a balance system that I made with wood and just stuff around the house, and we have two equal weights on both sides, and that's going to be a equal system. And in the second image I put the 2-pound weight at one end, and then I put two 2-pound weights in the middle of the other to create another equal system. We're going to have one box is equal to 907.185 grams, and that's also just the weights that I used in the example. And then the length of that would have been 6 feet, which is just 1.83 meters. So as you can see, this is going to be the pivot point, or the hinge, and then this can be the wood beam, and we're going to have two equal weights, equal distances apart from the middle, and the sum of torques for this is going to be equal to 0. And I also showed my calculations. So from the middle to where this weight would have been is going to be 0.915 meters multiplied by one weight, which is just right here, and it would come out to 830 Newton meters. And since this torque is going to be causing a counterclockwise, which is a positive torque, and this is going to be pulling or causing the object to move this way in a clockwise direction, that's gonna cause the net torques equal to 0. And so no motion, this is just gonna be an equal system. So for the next one, we're going to leave the weight on the right the same, and on the left we're gonna double the mass, but we're gonna pull it in closer to the point of contact. So we're gonna have 0.4575 meters away from the hinge. We're gonna multiply that by double the mass, and then we're just gonna have the same thing that we had in the first problem. And it turns out that they're both equal to 830 Newton meters. So the net torque, or the sum of torques, is gonna be equal to 0 in this as well.